Hello and welcome once again in this today's session, in this today's video. I'm going to solve some couple of questions which are based on the numericals from the magnetic, not from the magnetic, from the gravitational and the electrostatic fields. Okay. So these are some 4 questions based on gravitational force and electrostatic force. Okay. So 4 questions I am going to solve today in front of you. So these are from the Ibdp curriculum. Okay. And these have been taken from a book. Okay. Called book by David Holmer. Okay. And this is the 5th edition. Right. From this book I have selected these questions. Okay. So let us get started. This is your question number 1. This is question number 2. Okay. So let us get started with question number 1. Question number 1 says that two masses 5.4 kg and 1.2 kg are initially at a distance of 0.25 meters. Okay. Center to center. Calculate A, the mutual force of attraction between the masses. B, the distance between the masses when the force is 1.0 into 10 raised to a minus 9 Newton. So basically, in this question, now this is based on the gravitational field because they have asked you for the, they have given you the masses of the object. Okay, so it is related to gravitational forces, right? So two masses, so let us take two masses to be like M1 and M2. Okay, M1 and M2, and these two masses, you know, they are separated by a distance of say 0.25 meters. Okay, right, and the masses are 5.4 kg and 1.2 kg. Right, this is the information given in the question. Now A part of the question is the mutual force of attraction between the masses. Now, you know, the gravitational force is only a force of attraction. There's no question of repulsion. Okay. So you have to find the gravitational force of attraction between the two masses, these two masses. Okay. So your force Fg, I'll denote this gravitational force by Fg. This is given by the formula capital G, which is your gravitational constant, universal gravitational constant, times your M1 times M2, the whole thing divided by the R square. Okay, the R is nothing but the distance between the two masses, okay, which is 0.25 meters in this case. Now let us substitute the values. So G is 6.67 into 10 raised to minus 11 times one of the masses is 5.4, the other one is 1.2. Remember, you have to take the masses in kg. Okay, divided by the R square. R is 0.25, so it will be 0.25 the whole square. And remember that the distance also should be taken in meters only. Okay, so the masses should be in kg, the distance should be in meter. If they are not in kg or in meter, you have to do that. You have to bring them in kg and meter and then plug in the values. Okay, so let us do the calculation. This will be equal to, so we are finding Fg, okay, gravitational force. So this can be now written as now let me arrange this as 6.67 times 5.4 times 1.2, and this 10 raised to minus 11 I am taking extremely to the right hand side, divided by now the 0.25 square can be written as 25 upon 100 the whole square. Okay, right, so this can be written as 625 upon 10 raised to 4. Okay, and this can be otherwise written as 625 into 10 raised to minus 4. Okay. So I will remove this and I'm writing only 6.25 into 10 raised to minus 4. Okay. I hope you understand what I'm doing. Fine. Okay. Now your Fg will be equal to, now if you work out this part, okay, this part, it works out to 43.2216, that divided by this 625 times this, 10 raised to minus 11 upon 10 raised to minus 4 can be written as 10 raised to minus 11 plus 4. Okay. So ultimately your Fg will be equal to, on the calculator if I do this, I get it as 0.06915 times 10 raised to minus 11 plus 4 is minus 7. Okay. And of course the unit will be Newton because force is measured in Newton. Okay. So that is the answer, but it doesn't look good, so we'll bring it in the scientific notation form. So in scientific notation form, I will try to bring this decimal point after 6. So let me do that. 6.9 into, when I want to bring this decimal point over here after 6, I have to multiply it by 100. It has to move 2 places. When I multiply by 100, I have to also divide by 100. So dividing by 100 will make it 10 raised to minus 7 upon 10 raised to 2. Okay. So this answer will be ultimately written as 6.9 into 10 raised to minus 9 Newton. Is that okay? So the force, that is A part was asked, is what is the force between the two masses. Okay. So the force of attraction between the two masses we have found out to be this much. Okay. Now B part of the question. B part of the question says that find the distance between the masses when the force is 1.0 into 10 raised to minus 9 Newton. Now, keeping all the things as it is, only thing is you assume that the force now, the gravitational force now is 1.0 into 10 raised to minus 9. Okay, if this is the force and the mass is remaining same, okay, that is 5.4 kg and 1.2 kg. Now we have to find out what is this distance r. Okay. So in the same formula, that is Fg equal to G m1 m2 over the r square. In this formula, what I'll do is I'm going to put Fs 1 into 10 raised to minus 9. Okay, that is this force, right? This should be equal to 6.67 times, the masses are remaining same, so 5.4 kg times 1.2 kg, whole thing divided by r square. Now this time we want to find out r. Okay, so that is the unknown. Fine. Now if you arrange this, you will get r square equal to 6.67 into this will be 6.67 into 10 raised to minus 11 as well. Okay, right? So this will be 6.67 into 5.4 into 1.2 into 10 raised to minus 11 divided by this 1 into 10 raised to minus 9 will come in the denominator. Okay, 10 raised to minus 9. Right. Okay. Now if you work out this, you should get r square equal to, now if you work out just this much part, okay, you will get the answer as r square you are getting here. It's 43.22 16 times, now this is 10 raised to minus 11 and this minus 9 will go up and become plus 9. So minus 11 plus 9 is 10 raised to minus 2. Got it? So this can be written as 0.432216. Okay, because into 10 raised to minus 2 means divided by 100. So you will get this. So this is your r square. But you want to find out r. So what will be your r? Basically your r will be equal to square root of 0.432216. And this, you go on the calculator to find out this. First you will get 0.657 meters. And if you round this, you should get 0.66 meters, right? So that's your final answer, right? So the distance should be 0.66 meter. Okay. Now let us try to work out question number 2. Question number 2. I'm trying to save space, but then I think I should not do that. Okay, I'll be working out this over here. So this is my question number 2. Fine. Question number 2. Okay. Now, question number 2 says that a body of mass 7.4 kg is at a distance of 4.0 into 10 raised to 5. Is it 5 or yeah, 10 raised to 5 meter from the center of a spherical asteroid. The force of attraction between the body and the asteroid is 5.0 into 10 raised to minus 7 Newton. Okay, yeah, 10 raised to minus 7 Newton. Calculate A, the mass of the asteroid, and B, the gravitational field strength due to the asteroid on the at the position of the body. Okay, so he is talking about an asteroid which is having a mass, say capital M, and a body of mass 7.4 kg, another mass small m. This is 7.4 kg small m, and this mass is a body of mass 7.4 kg is at a distance of 4.0 into 10 raised to, so this distance, okay, r is equal to 4 into 10 raised to minus, is it minus? No, 4 is 10 raised to 5 meters. Okay, so your r is 4 into 10 raised to 5 meter. This is the distance between the two. This is your asteroids. Okay, this is your asteroid. Okay. Now a force of attraction between the body and the asteroid is, so force is also given to you, the force of attraction, gravitational force of attraction between these two is given to you as 5 times 10 raised to a minus 7 Newton. Having given all these things, you have to calculate A, the mass of the asteroid. So you have to calculate what is small m equal to. Oh, the mass of the asteroid, capital M, right? Small m is given to you. You have to calculate what is the mass of the asteroid. Capital M is equal to what? That you have to find out. Okay. So let us get started with the A part of the question. So we'll be using the same formula. Okay. So let us do the solution. So Fg is equal to G capital M small m divided by r square. That is equal to 6.67 into 10 raised to minus 11 into capital M into small m, you can take as 7.4, whole thing divided by r square, which is 5 into 10 raised to minus 7 the whole square. See here, the mass you have to keep in kg and the distance in meters, and because 7.4 kg, and this 5 into 10 raised to minus 7 are given in kg and meter respectively, so I don't have to make any changes, right? Now, this particular force, no, I'm so sorry, this R is not 5 into 10 raised to minus 7, rather your R is the distance, okay, that is 4 into 10 raised to 5 meter. So this will be 4 into 10 raised to 5 the whole square, and your force given is 5 into 10 raised to minus 7, right? So in this equation you have to find out this capital M. So on rearranging it, making M the subject, what you get is capital M is equal to 5.0 into 10 raised to minus 7 times 4 into 10 raised to 5 the whole square, whole thing divided by 6.67 into 10 raised to a minus 11 times a 7.4. Got it? So now this can be arranged and written as 5.0 into 4 square is 16 into 10 raised to minus 7 into 10 raised to 5 the whole square is 10 raised to 10. Okay, this is 10 raised to minus 7. Whole thing divided by, now here 6.67 I'll take along with 7.4 multiplied by 7.4 times 10 raised to a minus 11. Okay, so all these 10 powers I'm going to deal with together. So my capital M happens to be now 5.0 into 16 divided by 6.67 into 7.4. This will give me 1 point on the calculator. This will give me 1.6208. Okay, 1.6208. And this 10 powers, they will work out to 10 raised to minus 7 plus 10 is 10 raised to 3. And this minus 11 will go up and it will come plus 11. So 3 plus 11 is 14. So this becomes 10 raised to 14. Okay. So this is my answer and it will be in kg. And since this is already in scientific notation, okay, I don't have to make any changes. So the mass of the asteroid capital M is this. Okay. So that is A part of the question. Now B part of the question is the gravitational field strength. You have to calculate the gravitational field strength due to the asteroid at the position of the body. So this is that body of mass 7.4 kg at this particular position, that is at the distance of 4 into 10 raised to 5 meter from the asteroid. You have to find out what is the gravitational field strength. Now what is gravitational field strength? Gravitational field strength is denoted by a small g. Okay, this is your gravitational field strength, and this can be worked out by various formulas. The fundamental formula is, by definition, gravitational field strength is the gravitational force per unit mass. Now which mass you have to take? The mass of the body. Okay, which body? The smaller body. Okay, which is placed at a distance of 4 into 10 raised to 5 meters. Okay, you should not do the mistake of putting this capital M in this formula. Okay, capital M is the asteroid. It is creating the gravitational field. Okay, and the question asked is, find the gravitational field strength due to the asteroid at the position of the body. So you have to take the mass of the body into consideration in this formula. So G being that, now what is Fg? Fg is given to you as 5 into 10 raised to minus 7 Newton. Am I right? Let's check it. Yeah, it is given here. The force of attraction between the asteroid and the body is 5 into 10 raised to minus 7 Newton divided by, what is the mass of the small body? Mass of the small body, small m, is 7.4 kg. Okay, is that okay? This is in Newton, this is in kg, right? So when you do this calculation, 5 divided by 7.4, you get 0.67567, okay, times 10 raised to minus 7 is already there, and the unit will be Newton per kg. Am I right? Newton per kg. Okay. Now this isn't in the scientific notation form, so let me write in the proper scientific notation form. I will have to bring this decimal one place to the right. So this makes it 6.75 into 10 raised to minus 7. Now to bring here, I have to multiply by 10. So I have to divide this by 10. Okay. So this will be my answer. So this works out to 6. Now if you round this, 6.75 can be written as 6.8. Right? 6.75 can be written as 6.8 times 10 raised to a minus 7 minus 1. That is minus 8. Okay. Alright. So it will be 6.8 into 10 raised to minus 7. I think I made some mistake over here. 0.675, right? So 6 minus 7, it should be 0.675. So if I bring it over here, it will be 10 raised to 2. Okay. If I want to bring this, I'll do one thing. This decimal point, I'm going to bring it at this point, 67.5, right? I can do that, 6.7, right? So 6.7 into 10 raised to minus 7, and to bring this once again, I've made it 6.7, and I want to make it 6.8, right? 6.7 into minus 7 minus 1 is minus 8. Okay, it should be minus 8. Okay, let me check it. Fine. So it is going to be 6.8 into 10 raised to minus 8 Newton per kg. Okay, and you should know that G also has an alternate unit of meter per second square. Okay, so your answer can also be written as G equal to 6.8 into 10 raised to a minus 8 meter per second square. Okay, so either the unit is Newton per kg or meter per second square. Both units are workable. Okay, because G can have both these units, Newton per kg as well as meter per second square. But the numerical value is 6.8 into 10 raised to a minus 8. Okay, fine. So that was our question number 2. Right? Now in this today's session, I'm going to do only these 2 questions. In the next video, I'll be dealing with 2 more questions. Okay. So time is not permitting me to go ahead. So I'll stop here only. Okay. Here, I'm not sure whether it is 10 raised to minus 9 because 10 raised to minus 8 or 10 raised to minus 9. But this is a little doubtful. But as far as I'm concerned, I think this is the right answer because I'll have to verify the answer. Okay. Anyway, this is the answer. Right? That's all for today. See you in the next video very soon.